Divisibility interpreted in terms of congruence. Here's a term, n divides m. Everybody understand that, right? But what is now congruent version? M is congruent to 0 mod n. That's the same thing as n divides m, if you really think about it. Make sense? Yeah. So establishing this by calculating and using the mechanism of congruence, calculation mechanism, if you can establish that, that is the same as n divides m. Not necessarily factoring through and all that. Fair enough? All right. So here's a theorem. If your n, that's the modulus n there, is factored into prime factorization like that, and if you want to establish a is congruent to b mod n, you can actually separate this one into smaller modulus. It says it is equivalent to a is congruent to mod b for each of these prime power modulus. If you can establish this one, it'll imply that is actually a is congruent to b mod n. It's equivalent, right? So let me take a look at it like this. Suppose a is a massive expression. It's a mess. A is just like complicated expression with x in it, just like we did x squared minus x minus 2. And if we want to show this is equal to 0 or not, that means it's divisible by n, right? And you have to go through pretty much all the congruence classes. There's n classes. You have to test n classes, right? Which is equal to this product. But in the right-hand side, it says, oh, you don't have to do that. Just check this one. That will be P1 to the E1 checking, right? And the next one, P2 to the E2 checking. And if it passes all that, then there will be only the sum, P1 to the E1 plus P2 to the E2, all the way to the PK to the EK number of checking, right? And then you establish, oh, it is divisible or it is not divisible, right? So think about checking involves in there, number of checking is involved there, right? Which one's better? Obviously, this one's better, right? Involves less number of checking. However, getting this factorization is expensive, right? If you have that factorization, then it's hard. So you are the coder and you happen to have a factorization and you can do this kind of testing quickly, but the other guy doesn't know. They only know this n as this large this decimal expansion. The factoring will take months. So it's going to be a large and longer checking. It's embedded everywhere. And that's what I mean. Make sense? All right. I will leave this one to that one as as homework, but I think this one to that one is worth doing it here. So I want you to think about it here. Exercise number 1 is easier case. I'm going to write down easier case. Prove that if A is congruent to B, mod P and A is congruent to mod Q. I'm following their notation. P and Q I only had the parentheses around. Then we want to show A is congruent to mod what? P times Q, right? Where, what are the condition I want to put? P and Q are distinct prime or co-prime, right? Distinct primes. You are welcome to use a fundamental theorem arithmetic. You don't have to go back to the Bazoo's identity. If that's more convenient, you use that. Sometimes Bazoo's identity is more convenient. So you're asked to prove here that. Proof. All right. Make sense? The other direction is relatively easier. I will leave that as homework. How do you prove something is, I don't know, congruent to something? What was the very definition? Remainder is the same. That's right. Also, there was a lemma. Difference is divisible by that modulus there, right? Yeah. So I think that could be probably a little bit more convenient. Then you don't have to bring in the remainder and call it R1 and R2 and things like that. So if you can do that, you can reach that one using what formal mechanism? I word? Induction, right? Using induction, you can enter that. So, but we'll leave it here. This is more fun in here. All right, go ahead and try it. How's it going? All right, here's a minus b must have p in it, right? That's the same thing as a congruent to b. That's the lemma. A minus b must be divisible by p. So that's the statement there. A minus b is divisible by q as well, right? So we have that statement. And therefore, p is a factor of a minus b. Factors of, I forgot it, factors of what number? Common number, a minus b, right? And q is a factor of a minus b. And I wanted to conclude, if p is in there and q is in there, p times q is in there in a minus factorization of a minus p, right? Under what theorem can I conclude that? Fundamental theorem of arithmetic, right? That allows you to uniquely factors in there. Fundamental theorem of arithmetic. Why am I putting R in there? Because FTA means fundamental theorem of algebra. Okay? All right, any question? All right, you can extend this argument to more number of factors involved. Very good. Unique factorization. What's that one? All right, let's look at this neat problem. All right, you're asked to now prove this thing in here, degree 3 polynomial. Do you see that? A is an indeterminate or variable. A times A plus 1 times 2A plus 1 is divisible by 6 for every integer A. You're asked to prove that. So what is that we just learned? This is equal to, this thing is congruent to what number? Modulo what number? Mod 0 mod 6. This is what we wanted to establish, right? Do we really have to try all the every integers? No. What is it we have to try? A being 0 mod 6, 1 mod 6, 2 mod 6, 3 mod 6, 4 mod 6, 5 mod 6, right? Because all the numbers that fall into this class, that's all that matters in this congruence class calculation, right? Because of the well-definedness. So how many numbers to check? 6 numbers to check, right? Let's go through. 0, do you believe it? 0, plug it in. Everybody believes it. How about 1? How about 1? You see it? 1, 2 here is 1 there. Whew, we survived. 2 times 3, right? But everything else is pretty clear, right? No, not really. 2 there, that's 3. That picks up. So that works too, right? Yeah, yeah. 3 there. 3's there. And 3 plus 1, that gives you 2. So that gives up. So you can check it like that, right? All right. But what was the theorems we just proved? Oh, we can actually, you don't have to go through all that. We have to go through mod what? Mod 2 and mod 3. Isn't that the theorem? If you check mod 2, mod 3, it should be mod 6, right? But how many checkings involved there? 2 checking, 0 and 1, right? That's all you have to check. How about mod 3? 0 and 1 and 2, right? If you just check these 5 cases, we save 1 case. You don't have to check that one, right? But think about large number. It's a huge save. Let's try it. Mod 2, x equals 0, obvious, right? Mod 1, 1 mod 2, that goes in there, right? 0, so done. How about 0? 0 is right there, right? How about 1? 1 goes in there, that gives you 3, the check. 2 goes in there, check. So all 5 cases, you get always a 0 mod 2 or 0 mod 3, right? Therefore, we conclude that that thing is 0 mod 6. That is the use of the theorem. Yeah. So we saved 1, and everybody's so happy. We saved 1 case. Yeah. I'm glad you guys enjoying this theorem. Yeah, that's it. All right, there's more fun coming right here. Producing quick divisibility test. This is what you paid for. This is really lovely thing. All right, let's start with here. N is written like this as a decimal expansion. When I say decimal expansion, if you look at expressions like that, what kind of condition do you come to your mind to AK? This is integers ranging from where to where? 0 to 9, right? This is a power of 10s inserted there. So 123, we write it 1 plus 2 times 10 plus 3 times 10 squared, right? That expansion is correct. It is not entirely correct. What an expression. Sorry about that. 3 plus 2 times 10 plus 1 times 10 squared, right? It is a different direction, I realize. So increasing left to right. Right. So that's the decimal expansion, right? All right. We're going to come up with awesome divisibility test, right? You know when is it divisible by 2 and 5, right? That part's easy. Everybody knows that. So we're going to enter next thing. The theme is the following. Find M and S such that 10 to the S is congruent to epsilon mod M, where epsilon is 1 or negative 1. Okay? All right, we're going to start with the idea is that 10 to the epsilon appears here, right? 10 to the first, 10 to the second, and 10 to the third, 10 to the fourth, right? That can be replaced by what kind of number? Yes. Yeah, congruent to negative 1. Like 2 is congruent to negative 1 mod 3. Okay. Yeah, yeah, right, right. Okay, that's good. Right. So that's right, right? So this 10 to the epsilon will be replaced by 1 and negative 1, right? You go back in here, replace those 10 to the 10 to the s, 1 and negative 1. Anything that replaces 1 and negative 1, it's good. It reduces the size of the number enormously, right? That's the theme. It may yield really nice divisibility tests. Let's start with first case. All right. So how do we get that? It is about 1 on this side and negative 1 on that side, right? So if you bring that over, isn't that just 10 to the s minus epsilon, right? So this is 1 or negative 1. So I wrote down this 10 to the first minus 1, 10 to the first plus 1. And I factor them. It's a 3 squared, and that's 11, correct? Yeah. So you can turn this one into congruence relation. That means this is what we get out of that is the following. Isn't 10 congruent to 1 mod 3? I know you know this is true, but I want you to see that where it's coming from. It is coming from that. Do you see the manipulation? Right? 10 is equal to 1 plus 3 squared, right? Now if you enter modulus, that gives you 10 is congruent to 1 mod 3, correct? I hope you see that manipulation. So what else? What do you get here? 10 is congruent to negative 1 mod 11. You see that? Yeah, if you take a modulus 11, that's 0 congruent to 10 plus 1. The 10 is negative 1. If you look at this individual statement, it's obvious, easy. It's important that you understand where it's coming from so that you can enter more complicated one. Fair enough? Good. Let's not make a mistake in this case in here. Let's write it correctly. 3 goes first, right? What is the next one? 2 times the 10 to the first, right? And 3 times 10 squared, is that right? Go all the way up to what? Let's see, 1, 2, 3, 4, 5, 6. So you go all the way up to 10 to the 6th. Isn't that right? We want to calculate this modulus what? For example, 3, right? If we use this one. And if we want to conclude whether it's a 0 or not. If it is 0, it's divisible. Not 0, congruent to 0, not divisible, correct? All right. What comes to your mind? What do you want to do about this number? Using this one in here. All the 10s are replaced by 1, right? So can you write that? First number is 3, correct? What is the second number? 2. What is the third number? 3. Fourth number? Fourth next number? 5 and 1. Isn't that right? Please clap. This is amazing things you just noticed. That's Jeb Bush's quote, if you remember. All right. All right, let's go. Let's computing. This is congruent to this. Isn't that awesome? This is like gigantic number. Who wants to divide that by 3, right? Now you're down here. Let's reduce it by 3. Isn't that 0, 2, 0, 1, 0, what is it? 2 plus 1. Isn't that right? So keep going. What is this number? 6. Now we can clap. Wow, that's awesome. Yes, that's the proof. Yeah. Mod 3. Thank you. It's a good point. Yeah, 10. Yeah, all the tens of one. Exactly. Right. Wow, that is a. You should make a song out of it. Rap song. Tens of one sounds rhymes very nicely. Tens of one or tens of one, something like that. All right. All right. Understood the idea? All right. Why we stop in here? Keep going. What is the next one? Next one. 10 tens are negative one. Right? Tens are negative one. All the 10 is replaced by negative one. All right? Up for it? Okay, let's do it. There it is. Exercise. Exercise right there. First, try to pretend write down the powers. 1 plus 0 times 10 to the first, and replace all the tens with a negative 1. And you love it. Oh, yeah, let me, just, 10, what was it? Plus 1 is 11, right? This most profound statement we've seen today. And then is a 10 plus 1 is mod 11, right? So 10 is negative 1 mod 11. No, we're playing with the 10 to the first equals, um, we're playing with, this is a rule. We're going to play with this number. We're going to play with that number. And then we're going to play with this number. We're going to play that number. We're going to play with this number. We're going to play that number. That means you can replace the difficult powers of a 10 with a simple number 1 plus or minus 1, right? So this is the idea is given. So we're trying this two number first. There is 11. There is 9. In it, there is a 3 in there. So we could have pushed that divisibility of a 3 to the 9 as well, right? Because 9 divides 10 minus 1. All right? Let me help you with the beginning part. What is the beginning part? You write 1 plus 0 times 10 to the first, right? 6 times 10 squared. 4 times what? 10 to the third. Go on. Um, that's the third. 4, 5, 6, 7, 8, 9, 10. 10. Yeah, I was confused at the beginning. So I feel you. Right, this is the 0th place, that's the 10th place, and so on. Yeah. But why do I write it like this? I don't know. It's like Taylor series, you've got used to it. Something like that. Forget what I just said. Because 10 is congruent to -1. So if you square it, like you squared -1, yeah, you have 50-50 chance, divisible or not. You'll get it. But the alternating pattern, to pick up the alternating pattern, you look at the digit, flip the sign at the bottom. Right. That is the coolest thing, right? Let's move on to the next level. Is that right? Any question? It's written down there. Yes? Right. That's why I'm going for this one, next one. Whatever appears inside there will offer us cool divisibility test. It has to be, idea is replacing powers of 10 with the 1 and -1, right? Whatever the number is hidden inside, we'll discover it. So let's go to the next level. 10 squared plus 1, 10 squared minus 1. What's in it, right? If 13's in it, then 10 squared will be replaced by 1, right? So you can go skipping one digit and you can replace that with 1. All right, let's hear it is. So I did that, and here's it. Yes. This is a positive and that's negative, alternating. Started with the positive, next one negative, positive, negative, because that's the power of 10 that is congruent to -1 to the end. Second, so you start with a positive. That's it. Yeah. 6 minus 4. Oh, we're combining whatever they cancel each other. Why am I combining a certain way? Is that what you're saying? 2, that's right. Whatever they cancel each other, so keep the magnitude of number small. That was my gut instinct at the moment. I wasn't planning to talk about it, but that's what I did. Yeah. All right, good. What's the next level? Is this secret. 10 squared minus 1. What's in it? 11. Still in it, right? There's nothing new in it, right? Why am I saying that? Because 3 and 11, we already had it, right? And 101, not so fun. It's a 3-digit prime number. So I'm moving on to the next one to have more fun with it. And to the third, what do you see in it? 37 is in it, right? And 7 is in it. I like that. Did you know about the divisibility test of 7? No. So we're going to discover it. So let's enter divisibility test of 7. 10 to the third is what congruent to mod 7? You don't need a calculator. There is this equation. -1, right? So going every third block, you'll be able to replace that. So 10 to the third is going to be replaced by -1. What is the next one that you can do? 10 to the sixth, right? That's easy. What is it? +1 if you square it, right? How about 10 to the, what is the next one? Is a 9, that's right, yeah. And that's going to be -1, right? By keep multiplying 10 to the third in there. So you can't change the 10 to the first and 10 to the second, but you can change the 10 to the third, you can change the 10 to the sixth, you can change the 10 to the ninth, like that, right? Fair enough? All right, let's try it. There it is. Was it 7, right? Did I do the 7? I don't even have that 7. So I was wrong. I was doing 13, but that's the same thing. Instead of 7, I chose 13 down there. All right, let's try it. But the congruence is the same. All right, so here's the exercise, and I'm just changing the 7 to 13 and pointing 13 there. So 13 is there. So if you reduce a modulo 13, 10 to the third is -1. There is a 1, 2, 3, 4, 5, 6, 7, 8-digit number, and write down and the power expansion form. Every time you do 10 to the third, 10 to the sixth. Also, I'm going to help you on that one. I think that helps you. Is exercise 3? So let's do this together. At the beginning, it starts like this: 7 and 1 times 10 to the first, 5 times 10 squared, right? The next one is 715, 847, 8, 4, and 7. So here's the trick. Beginning here, you can pull out 10 to the third, right? I hope you see that. It's times 10 to the first, and that's 10 to the second, right? Yeah. And then if you pull out another 10 to the sixth there, that's a 5 and 6. 7, 2, and 6 is a 2 times 6 times a 10 to the first. So 1, 2, 3, 4, 5, 6, 7. That's correct. So if I pull out like this, and it's easier to see what's happening. So take it from here. By 13, yes. Yes. Or 13. Everything works, yes. Yeah. Oh, that's why it was weird. So that's 1 there, right? So that's 1. What does that become then? 9 and 3 is at 7. 169, right? Yeah, it's 169. Awesome. Awesome. Yes. Yes. Go ahead. We don't have that statement. Only 10 to the third is a negative 1. Yeah. So you have to can't touch that, but when you hit the 10 to the third, you can replace the negative 1 and organize a little bit, and then that helps you to that process. Go ahead. Yeah. So knowing that it's a third part, you can just block it 3 like that, and then turn it into a 3-digit number with an alternating sign. That's the divisibility test of 13. It's not very popular. Not many people know this. How about divisibility of 7? You can do that too. Divisibility of a 37 is even better, right? It's all ones, right? So Got the idea?